Hello, sleepy soul. Welcome to this quiet corner of the cosmos. If you're hearing this now, in the deep hours of the night, let yourself settle. Let your shoulders drop. Let the weight of the day just drift away. Tonight, we're going to wander together through the ending chapters of stars, through white dwarfs and black dwarfs, through stellar fossils that hold the memory of light from billions of years ago. But there's no hurry, no test at the end, nothing you need to remember. This is just a soft voice and some gentle fact about the universe to keep you company as you drift. Let your eyes relax. You can close them now if you'd like. The screen doesn't matter. The only thing that matters is rest. Let your breathing slow. In and out. In and out. We have over 2 hours together. 100 facts. But you won't hear them all. You're not supposed to. This is designed for sleep, for letting go, for allowing your mind to wander away from worry and into the vastness of space. So settle in, get comfortable, and let's begin this slow journey into the quiet ending of stars. Out there in the velvet darkness between the stars, there are objects so strange, so dense, so quietly beautiful that they almost defy imagination. They are called white dwarfs. And someday, trillions of years from now, when the universe has grown cold and dark, they will become black dwarfs. These are not the bright, burning stars you see in the night sky. These are the embers, the remains, the fossils of stars that once shone, but now have entered a kind of cosmic sleep. A white dwarf is what happens when a star like our sun reaches the end of its life, when the fuel runs out, when the fire finally goes quiet. What remains is something small, something dense, something that glows not from new energy, but from the memory of heat, like a stone pulled from fire, still warm to the touch, even though the flames have long since gone. And a black dwarf, well, a black dwarf is what comes after even that warmth fades, after trillions of years, after the universe itself has grown old and cold. But we're getting ahead of ourselves. Let's start at the beginning, or rather at the ending of a star. Take a slow breath in and out, and let's drift together into the first fact. White dwarfs and black dwarfs are what astronomers call stellar fossils. Imagine finding an ancient shell on a beach, millions of years old, hardened by time, still holding the exact shape of the creature that once lived inside it. That shell tells a story about the ocean, about the animal, about a moment frozen in time. White dwarfs are like that. They preserve the chemical composition of the star they came from. Locked inside that tiny, dense core is the history of billions of years of fusion, of helium burning into carbon, of carbon and oxygen settling into layers. Scientists can look at a white dwarf and read its composition like a book. They can see what elements were created, what the star was made of, how it lived, and someday when these white dwarfs cool into black dwarfs, they will still hold that record for trillions of years, long after galaxies have faded, long after new stars have stopped forming. They are cosmic time capsules, quiet, dense, unchanging, fossils of light. Now, let's talk about something that sounds impossible. A white dwarf is roughly the size of Earth, about 12,000 kilometers across. You could almost hold one in your mind. Picture our whole planet, all the oceans, all the mountains, all the life. But here's the astonishing part. A white dwarf contains the mass of the sun, the entire sun, all of its matter, compressed down into something the size of our world. This makes white dwarfs incredibly dense, about 1 million times denser than Earth. If you could take a teaspoon of white dwarf material, just one small teaspoon, it will weigh about 5 tons, as much as an elephant. In a teaspoon, the gravity would be immense. If you try to stand on the surface of a white dwarf, you would be flattened instantly. The pull would be hundreds of thousands of times stronger than Earth's gravity. But of course, you're not standing anywhere right now. You're lying down, safe, comfortable, letting this strange, distant universe wash over you like a lullaby. Breathe slowly, in and out. White dwarfs glow, not because they're still burning fuel, not because fusion is happening in their cores. Those fires went out long ago. They glow from residual heat. Imagine a blacksmith's forge, the coals glowing red, orange, white hot. Now imagine the blacksmith walks away. The fire is not fed. Slowly, over hours, the coals cool. But for a long time, they still glow, still radiate heat into the darkness. White dwarfs are like that. They are cooling embers. When a white dwarf first forms, its surface temperature can exceed 100,000 degrees Celsius, hotter than the surface of most living stars. It shines with a brilliant white light, not from creation, but from memory. Slowly, over millions, then billions, then trillions of years, the heat radiates away into space. The white dwarf cools, dims, changes color from white to yellow to red to infrared to nothing. But that process is so slow, so patient, so gentle. There is no rush in the death of a star. Now here's where things become strange. You might wonder, what holds a white dwarf up? What prevents it from collapsing under its own enormous gravity? The answer is something called electron degeneracy pressure. This is a quantum effect, a rule from the deepest layer of physics. Electrons, those tiny particles that orbit atoms, obey a principle called the Pauli exclusion principle. It says that no two electrons can occupy the same quantum state. They resist being squeezed too close together, not because of force exactly, but because of the nature reality itself. In a white dwarf, electrons are packed so tightly that they push back. They refuse to be compressed further. This pressure, this quantum stubbornness, holds a star up, but there's a limit. If a white dwarf exceeds about 1.4 times the mass of the Sun, a threshold called the Chandrasekhar limit, the electron pressure fails, the quantum rule breaks, and the star collapses. What happens then is not gentle. It is a violent explosion, a type Ia supernova. The white dwarf is obliterated, blown apart in one brilliant, catastrophic flash. But most white dwarfs never reach that limit. They simply cool and wait and wait and wait. Let's talk now about black dwarfs. These are white dwarfs that have cooled completely, cooled so much that they no longer emit any light. No heat, no radiation. They would be invisible, dark, cold, hovering near absolute zero, negative 273 degrees Celsius. A black dwarf is what a white dwarf becomes after it has been cooling for trillions upon trillions of years. But here's the thing. Black dwarfs are theoretical. They don't exist yet. Not a single one. Anywhere in the universe, because the universe is too young. The universe is roughly 14 billion years old. That sounds like a long time, and it is. Galaxies have formed, stars have lived and died, planets have circled their suns, life has emerged, but in the scale of stellar cooling, 14 billion years is nothing. It takes tens of billions of years for a white dwarf to cool significantly, and trillions of years, perhaps 100 trillion years or more, for it to reach the cold, dark state of a black dwarf. The universe hasn't been around long enough, not even close. So every white dwarf you can see, every single one, is still glowing, still warm, still radiating the memory of its fire. The first black dwarf won't form for eons beyond imagining. Long after the last stars have burned out, long after galaxies have dissolved, long after the universe has become a cold, dark, quiet place. But someday, black dwarf will exist. Silent, invisible, the final tombstones of the stars. White dwarfs form from stars like our sun. When a sun-like star reaches old age, it runs out of hydrogen fuel in its core. It begins to die, but it does not go quietly. First, it swells. It becomes a red giant, huge, bloated. Its outer layers expand outward, sometimes swallowing the inner planets. Then, in a final act, the star sheds those outer layers. It puffs them off into space in great, glowing shells of gas. This creates what we call a planetary nebula, a beautiful cloud of ionized gas, lit from within by the hot coal of the dying star. And that core, the leftover center, is the white dwarf. It's what remains when the outer layers are gone. A dense ball of carbon and oxygen, too light to continue fusion, too stubborn to collapse. It just sits there, cooling, a stellar ember in a cloud of its own making. In about 5 to 7 billion years, our sun will become a white dwarf. It will happen slowly. So slowly. First, The sun will burn through its hydrogen. It will swell into a red giant. It will engulf Mercury, maybe Venus, possibly Earth. Then it will shed its outer atmosphere. The beautiful gases will drift away, forming a nebula around a tiny, hot core that remains. And that core will be a white dwarf, about the size of Earth, containing half the sun's current mass. It will glow white-hot at first, then yellow, then red. It will cool over billions of years, slowly dimming, slowly fading. And if the universe lasts long enough, if time itself continues, that white dwarf will one day become a black dwarf, our sun's final form. Cold, dark, silent, but that is so far away, so unimaginably distant. For now, the sun still shines, warm on your face during the day, and you, right now, are simply resting, safe, breathing slowly, in and out. Not all white dwarfs are the same. Some are smaller, lighter, less than 0.2 times the mass of the sun. These low-mass white dwarfs are unusual. They often form in binary star systems, where two stars orbit each other closely. In these systems, one star can steal mass from its companion, stripping away the outer layers before the core has finished contracting. What remains is a helium white dwarf, bloated, larger than a typical white dwarf, still slowly settling. These helium white dwarfs can take up to 2 billion years just to fully contract to their final size. 2 billion years. That's half the age of Earth, spent just shrinking, cooling, settling into a stable state. There is no rush in the cosmos, no impatience, just slow, patient transformation. Helium white dwarfs are special. They form when a red dwarf, a small, dim star, loses its outer hydrogen envelope in a binary system. The process is called stable Roche lobe overflow. The red dwarf's companion pulls material away, gently, steadily, until only the helium core remains. Because these white dwarfs lack hydrogen shells, they behave differently. They don't experience nova outbursts, no sudden flares, no explosions. They are quiet, stable, predictable, just small, dense spheres of helium, cooling slowly, orbiting their companion stars in silence. In the vast darkness of space, these helium white dwarfs spin, patient, enduring, waiting for the long, slow march of time to cool them, dim them, and eventually, after trillions of years, turn them into black dwarfs. But that time is so far away. For now, they simply exist, glowing faintly, spinning slowly. Like everything in the universe, they are in no hurry, and neither are you. Let your breathing deepen. Let your muscles relax. You are safe. You are resting. And the universe, the vast, patient universe, continues its slow dance around you in the far reaches of the galaxy. In regions where metals are scarce, something unusual happens. Red clump stars, These are stars in a particular phase of their evolution, burning helium in their cores after a sudden ignition called the core flash. In most environments, these stars would pass through what astronomers call the horizontal branch, a phase of gradual burning, a pause in their journey. But in metal-poor regions, where the primordial gas still holds sway, red clumped stars skip that step entirely. They evolve directly, straight down into helium-white dwarfs. No detours, no extra phases, just a simple, direct transformation from a helium-burning giant to a cooling helium ember. It's a reminder that not all stars follow the same path. The chemistry of their birth environment, the trace elements present when they formed, shapes their entire life story. And even in death, that story is preserved in the quiet glow of a helium-white dwarf, somewhere in the outer halo of the galaxy, cooled over billions of years. If you look up on a clear winter night, you might see Sirius, the brightest star in the sky. But Sirius is not alone. Orbiting it, invisible to the naked eye, is Sirius B, a white dwarf, the nearest white dwarf to Earth, just 8.6 light years away. Sirius B was discovered in 1844, not by seeing it directly, but by watching Sirius wobble. The main star moves slightly, tugged by an unseen companion. Decades later, in 1862, astronomers finally saw Sirius B through a telescope, a faint point of light, incredibly dense, orbiting its bright companion every 50 years. Sirius B descended from a B-type star, a massive, hot star that burned through its fuel quickly. It lived fast and died young, leaving behind this tiny ember. Today, Sirius B is roughly the size of Earth, but contains almost the entire mass of the Sun. It's cooling, dimming, spinning silently through space, forever bound to the brilliant Sirius A, a reminder that even the brightest stars have shadows, and even shadows have stories. Some white dwarfs carry secrets in their composition. When they form from asymptotic giant branch stars in the late stages of life, something special happened deep inside. Neutrons were slowly captured by atomic nuclei, one by one, building heavier elements through a process called the S process. The S stand for slow. Elements like barium, strontium, lead, created not in explosions, but in the quiet, patient interior of a dying star. When the star shed its outer layers and became a white dwarf, these S-process elements remained, locked into the cooling core, preserved. Astronomers can detect these elements. They can read the signatures in the white dwarf spectrum, and from those signatures, they can trace back the nucleosynthesis that happened billions of years ago. It's like finding ancient writing on a stone. The stone is the white dwarf. The writing is the memory of nuclear reactions, the slow capture of neutrons, the building of atoms, one patient step at a time. Even in death, the star tells its story. Most white dwarfs, the ones that form from sun-like stars, have cores made of carbon and oxygen. This is the ash of helium burning. When a star fuses helium in its core, it creates carbon. Then, if conditions are right, it fuses more helium with carbon to make oxygen. But the star is not massive enough to ignite carbon fusion. The temperature never gets high enough. The pressure never becomes intense enough. So the carbon and oxygen just sit there, inert, degenerate, packed tightly by quantum pressure. Above this core, there are thin layers. Sometimes a shell of helium, sometimes a trace of hydrogen, left over from the star's outer envelope. But the core, the heart of the white dwarf, is carbon and oxygen, crystallized over time, locked into a lattice structure as the star cools. Some astronomers like to say that old white dwarfs are essentially giant diamonds in space. Carbon, compressed, crystallized, cooling in the darkness. A cosmic jewel, invisible, silent, waiting. Not all white dwarfs have carbon-oxygen cores. The more massive ones, have cores made of oxygen, neon, and magnesium. These form from slightly heavier stars. Stars with masses between about 7 and 10 times the Sun. In these stars, the core becomes hot enough, dense enough to fuse carbon. When carbon fuses, it produces neon, oxygen, and magnesium. But even these heavier stars don't reach the threshold for neon fusion. They stop just short. And when they shed their outer layers, what remains is a white dwarf with an oxygen neon magnesium core. These white dwarfs are more massive than typical carbon-oxygen white dwarfs. They range from about 0.7 to 1.1 solar masses, closer to the Chandrasekhar limit, closer to the edge. If such a white dwarf accretes matter, pulls in gas from a companion star, it might reach that critical mass. And then it won't cool quietly. It will collapse, ignite, explode. But most simply cool, slowly, over eons. Another kind of ember, a different composition, but the same fate. Cooling, dimming, waiting for the universe to grow old. White dwarfs have a secret layer. Above the degenerate core, there is a thin envelope. So thin, barely 10 to the power of -15, 1/4 of the star's total mass. This envelope is made of hydrogen or helium, non-degenerate, almost normal matter. It acts as a blanket, an insulating layer. The core below is immensely hot, millions of degrees. The envelope above is cooler, only tens of thousands of degrees at the surface. This envelope controls the rate at which heat escapes. It regulates the slow leakage of gravitational energy, the residual warmth, into space. Without this envelope, the white dwarf would cool much faster. The heat would radiate away unchecked. But the envelope slows the process. It traps the heat. It allows the white dwarf to glow for billions of years. A thin shell, almost nothing, but crucial, like a blanket pulled over you on a cold night, keeping the warmth in. letting you rest comfortably. The white dwarf rests too, wrapped in its envelope, cooling slowly, in no hurry at all. Here is something that seems backwards at first. The more massive a white dwarf is, the smaller it becomes. In normal objects, if you add more mass, they get bigger. A bigger star, a larger planet. But white dwarfs are held up by electron degeneracy pressure, and that pressure responds strangely to mass. When you add more mass to a white dwarf, gravity increases, the core compresses. Electrons are squeezed closer together. The degeneracy pressure pushes back, but not enough to maintain the same size. The white dwarf shrinks. A white dwarf with 0.6 solar masses might be about the size of Earth, but a white dwarf with 1.2 solar masses might be only half that size. More mass, smaller radius. It's called a mass-radius relation, an inverse relationship. The closer a white dwarf gets to the Chandrasekhar limit, the more compressed it becomes, the smaller, the denser, until, if it crosses that limit, it can't shrink anymore. It collapses, but most never reach that point. They simply exist, dense, small, cooling, following the strange rules of quantum mechanics. Inside a white dwarf, something remarkable happens. The core reaches a nearly uniform temperature, not because of convection, not because of fusion, but because of the degenerate electrons. Electrons in a degenerate state have enormous thermal conductivity. They carry heat extremely efficiently, almost instantly spreading warmth throughout the core. So even though the surface of a white dwarf might be cooling, dropping from 100,000 degrees to 10,000 degrees over billions of years, the core stays at a relatively uniform temperature. For the first billion years or so, the core and surface are coupled. They cool together. But after about 10 to the power of 9 years, 1 billion years, they decouple. The core becomes nearly isothermal, the same temperature throughout, while the surface continues its slow, independent cooling. This decoupling changes how the white dwarf radiates. The surface temperature no longer directly reflects the core temperature. It's like a house with excellent insulation. The temperature inside stays stable, while the outside walls respond to the changing seasons. The white dwarf's core calm, uniform, patient, while the surface dims, cools, fades. In the early life of a white dwarf, the first few million years, something invisible is happening. Neutrinos are escaping. Neutrinos are ghostly particles. They barely interact with matter. They pass through the Earth, through your body, through entire stars without stopping. In a young white dwarf, nuclear reactions in the hot core produce neutrinos. These neutrinos stream out into space, carrying energy with them. This is called neutrino cooling. It happens rapidly, much faster than photon cooling. The slow radiation of light and heat from the surface. For the first few million years, neutrinos dominate the cooling process. The white dwarf loses energy quickly. The core temperature drops. But eventually, the core cools enough that neutrino production stops, and then photon cooling takes over. The slow, patient radiation of heat through the envelope into space. Neutrino cooling is like opening a window on a winter night. Heat rushes out quickly. Photon cooling is like the slow seep of warmth through insulated walls. Both happen, but at different times. And the white dwarf cools and cools and cools. Let's talk about something called Debye cooling. In the first billion years of a white dwarf's life, the core is extremely hot, 10 million degrees Kelvin or more. At these temperatures, the ions in the core, the carbon and oxygen nuclei, are vibrating intensely, jiggling with thermal energy. As the white dwarf cools, these vibrations slow down. The lattice of ions begins to settle. The thermal motion decreases. This process, the cooling of the ion lattice, is described by Debye theory. It's a model from solid-state physics. During this phase, neutrinos carry away energy. The core temperature drops from 10 million degrees down to a few million degrees. But here's the interesting part. Even as the core cools dramatically, the surface can stay hotter. The thin envelope insulates the interior. So you have a white dwarf with a core at, say, 5 million degrees, but a surface at 100,000 degrees. The gradient is steep. The insulation is effective. Debye cooling dominates the first billion years. Then gradually, photon cooling takes over, and the white dwarf enters a new phase, a slower phase, the long drift toward darkness. Breathe slowly, in and out. There is no rush, not for the white dwarf, not for you. Just rest, just drift. The universe is patient, and so are you. In the beginning, when a white dwarf is freshly formed, its interior is scorching hot. The core temperature can reach 100 million degrees Kelvin. 100 million. At first, the entire white dwarf cools uniformly. The degenerate electrons spread heat so efficiently that the inside stays at nearly the same temperature throughout. But the surface, the outer layers, radiate like a black body. A black body is an idealized object that absorbs all light and emits radiation based purely on its temperature. The white dwarf surface glows, white hot initially, radiating energy into space. And this is where the time scale becomes almost incomprehensible. It takes trillions of years, trillions, for a white dwarf to cool from 100 million degrees in the core down to near absolute zero. Trillions of years to dim from brilliant white to faint red to invisible black. The surface radiates steadily, patiently, photon by photon. The interior cools uniformly, slowly releasing its stored heat. And time, cosmic time, stretches out, longer than the current age of the universe, longer than galaxies will shine. The white dwarf simply waits, cooling, dimming, enduring, as a white dwarf ages. As it cools past certain temperature thresholds, something changes in its thin atmosphere. Convection begins. Convection is the process where hot material rises and cool material sinks, like water boiling in a pot, churning, circulating, in the thin hydrogen or helium envelope of an aging white dwarf. Convection enhances heat transport. It carries warmth from the deeper layers up to the surface more efficiently than radiation alone. This is a curious effect. The white dwarf's cooling, which had been smooth and predictable, suddenly plateaus. The luminosity stays relatively constant for a while. A pause, a brief hesitation in the long descent toward darkness. This is called the convective plateau. It happens because convection is so efficient at bringing heat to the surface. For a time, the star radiates more effectively. It maintains its brightness a little longer. But eventually, even convection cannot stop the inevitable. The white dwarf continues cooling. The plateau ends, and the slow fade resumes. A brief delay, a moment's pause, and then onward, downward, into the dark. Now we come to one of the most beautiful processes in the life of a white dwarf: crystallization. As the white dwarf cools, the ions in the core, the carbon and oxygen nuclei, begin to slow down. Their random thermal motion decreases, and at a certain temperature, around 10 million degrees Kelvin in the core, they lock into place. They form a crystal lattice, a solid structure, like water freezing into ice. But this is not ordinary ice. This is carbon and oxygen, crystallizing under immense pressure, forming something extraordinarily dense. When a material crystallizes, it releases latent heat, the energy that was stored in the random motion of particles is released as the structure becomes ordered. This latent heat slows the cooling process. The white dwarf releases this energy slowly, over millions of years, as more and more the core crystallizes. In more massive white dwarfs, where oxygen and neon dominate, the crystals might be oxygen-neon structures, different chemistry, but the same principle. Crystallization is a kind of second life, a brief reprieve. The white dwarf dims more slowly, held up by the release of this hidden energy. And then, once crystallization is complete, the cooling resumes its patient march. Inside some crystallizing white dwarfs, something even more subtle happens: phase separation. As the core crystallizes, carbon and oxygen don't mix uniformly. They separate. Oxygen, which is heavier, sinks toward the center. Carbon, which is lighter, rises toward the outer layers of the core. This creates a stratified structure, an oxygen-rich center, a carbon-rich shell around it. Phase separation releases additional gravitational energy. The heavier elements falling inward, the lighter elements floating upward, generates heat. This changes the cooling rate. It alters the thermal conductivity of the core. Heat flows differently through a layered structure than through a uniform mixture. Some models suggest that phase separation can delay cooling by up to 1 billion years. 1 billion years added to the white dwarf's glowing life, simply because the elements inside reorganize themselves, slowly, patiently, following the laws of thermodynamics: oxygen sinking, carbon rising, layer by layer. The white dwarf restructures itself, and time passes. There is something poetic about the fate of white dwarfs. As they cool, as their cores crystallize, the carbon inside arranges itself into a lattice under the immense pressure, trillions of times Earth's atmospheric pressure. Carbon crystallizes in the same structure as diamond, not diamond as we know it. These crystals are far denser, far harder, formed under conditions that no laboratory could replicate. But structurally, it's diamond. So in a sense, aging white dwarfs are giant cosmic diamonds, Earth-sized, invisible, floating in space. Some of the oldest white dwarfs, the ones that have been cooling for 10 billion years, may already have diamond cores, crystallized, solid, unchanging, and someday, when they become black dwarfs, they will still be diamonds, cold diamonds, dark diamonds, crystals in the void. No one will see them. No light will reflect off their facets, but they will exist, silent, perfect, eternal, the universe's hidden jewels. When a white dwarf cools below about 4,000 degrees Kelvin, something unusual happens in its atmosphere. At these low temperatures, hydrogen molecules begin to interact in strange ways. Normally, individual hydrogen molecules don't absorb much visible light. They're mostly transparent. But when they collide, when two hydrogen molecules come very close together, their quantum states interact. And during that brief collision, they can absorb light. This is called collision-induced absorption. It happens in the dense atmospheres of cool white dwarfs. The pressure is so high that collisions are frequent, and the result is surprising. These cool white dwarfs, which you might expect to look red or infrared, actually appear bluer than expected. The collision-induced absorption affects red wavelengths more than blue wavelengths. So the star spectrum shifts. It's a counterintuitive effect. A cool will start looking hotter than it is. A trick of quantum mechanics. A quirk of molecular collisions. The white dwarf dims, cools, but its color tells a more complex story. At around 3,000 degrees Kelvin, the atmosphere of a white dwarf undergoes another transformation. Molecular hydrogen, H2, forms in abundance. The pressure is so high, billions of times Earth's atmospheric pressure, that hydrogen atoms are forced together. They bond. They create molecules. These molecules have a profound effect. First, they broaden the spectral lines. Pressure broadening. The lines become wide, diffuse smears across the spectrum. Second, they shift the star's emission into the infrared. Molecular hydrogen radiates heat, but not visible light. the white dwarf becomes an infrared object, invisible to the eye, detectable only with specialized telescopes. Third, and this is crucial, molecular hydrogen quenches pulsations. Some white dwarfs pulsate. They vibrate like bells, expanding and contracting rhythmically. But molecular hydrogen dampens these vibrations. The atmosphere becomes too opaque, too dense. The pulsations fade. The white dwarf falls silent. No more oscillations. No more rhythmic changes. Just a steady, slow fade into the infrared. A quiet ending. A gentle dimming. Deep inside a cooling white dwarf, as crystallization spreads, there's a moving boundary, a crystallization front. This front propagates outward, starting from the center, where the core is coolest and densest, and moving slowly toward the surface layers. As this front moves, as ions lock into crystal lattice, there are brief nuclear reactions in some intermediate mass white dwarfs. These reactions produce muons, exotic particles, heavier cousins of electrons. These muons decay rapidly, and when they decay, they emit neutrinos. For a brief period, millions of years, perhaps, the white dwarf's neutrino luminosity increases. It's a small effect, invisible. The neutrinos stream away into space, undetected. But it's there, a ghost of nuclear activity, a final whisper of particle physics, in an otherwise quiet, cooling star. The crystallization front moves. The muons decay, the neutrinos escape, and the white dwarf continues cooling, unaware, unchanging, just cooling. Imagine a white dwarf that is cool for eons, trillions of years. The universe is ancient, dark, cold. The white dwarf's interior, its crystallized core, has reached temperatures near 1,000 degree Kelvin, almost absolute zero. At these temperatures, the crystal lattice exhibits quantum plasticity. This means the crystal can slowly reconfigure itself, without fracturing, without breaking. If the white dwarf is in a binary system, if it's subjected to tidal stresses from companion, the crystal doesn't crack. Instead, it flows slowly, quantum mechanically. The lattice rearranges. Atoms shift positions over vast timescales, responding to external forces. It's a property unique to quantum solids, a strange, slow fluidity. The white dwarf, solid as diamond, yet able to deform, able to adapt, even at the edge of absolute zero, even in the deepest cold. The quantum universe retains its strangeness. The white dwarf endures, deforms, reconfigures, patiently, silently, in the cold, dark future of the cosmos. Not all white dwarfs look the same. Astronomers classify them by their atmospheres, by what elements appear in their spectra. The most common type is Da. About 85% of all white dwarfs are Da types. Their atmospheres show strong hydrogen lines. The hydrogen absorbs specific wavelengths of light, creating dark lines in the spectrum. These are the classic white dwarfs, hydrogen envelopes. Simple, clean. Then there are DB white dwarfs. These show helium in their atmospheres. No hydrogen, just helium lines. How does this happen? Sometimes hydrogen is blown away by stellar winds. Sometimes it's mixed down into the core by diffusion. The surface becomes helium-dominated. And then there are the DZ types. These are polluted white dwarfs. Their atmospheres contain metals, not just hydrogen or helium, but calcium, magnesium, iron, silicon. Where do these metals come from? From debris, from asteroids, comets, or shattered planets that once orbited the star. When the star became a red giant, it disrupted its planetary system. Rocky bodies were scattered. Some fell inward, and over millions of years, these rocky fragments spiraled into the white dwarf. They vaporized. Their elements mixed into the atmosphere. The white dwarf spectrum now contains a signature of dead worlds, the remnants of planets, the ash of asteroids, a graveyard preserved in light. Some white dwarfs are difficult to classify. They show no spectral lines at all, no hydrogen lines, no helium lines, no absorption features, just a smooth, continuous spectrum. These are called DC white dwarfs. The C stands for continuous. This happens when the white dwarf has a helium atmosphere, but it's either too hot or too cool for helium lines to form strongly. At very high temperatures, the helium is ionized. The electrons are stripped away. No lines. At very low temperatures, the helium is neutral, but the energy levels don't produce strong visible absorption, so the spectrum is featureless. To classify these white dwarfs, astronomers rely on other methods. Photometry, measuring brightness in different filters. Parallax, measuring distance and inferring properties. It's detective work, piecing together clues from faint, distant light. The DC white dwarfs are still there, still cooling, still glowing faintly, but their atmospheres offer no direct spectral signature. They are quiet, anonymous, smooth, like a blank page, a surface with no writing, just light, fading, slowly. Then there are the DQ white dwarfs. These show carbon in their spectra, carbon lines, sometimes atomic carbon, sometimes molecular carbon, CH bands. This is unusual. White dwarfs are supposed to have pure hydrogen or helium atmospheres. Where does the carbon come from? The answer is convection. In some white dwarfs, especially those cooling through certain temperature ranges, convective currents form in the envelope. These currents dredge up material from deeper layers. They bring carbon from the core or from deeper envelope layers up to the photosphere. The surface becomes polluted with carbon. At temperatures around 7,000 degrees Kelvin, the carbon forms molecules, CH, carbon-hydrogen bonds. These molecules create absorption bands in the spectrum. dark smears across certain wavelengths. The white dwarf spectrum becomes marked, distinctive. It's a window into the interior, a glimpse of the carbon-oxygen core, brought to the surface by slow, churning convection. The white dwarf cools. The convection continues. The carbon remains visible, a signature, a chemical fingerprint. We've mentioned DZ white dwarfs before, but let's go deeper. These white dwarfs show calcium and magnesium in their atmospheres. Sometimes iron, sometimes silicon. These are metals, heavy elements. They don't belong there. Hydrogen and helium are light. They should float at the surface. Metals should sink, pulled down by gravity, diffusing into the deeper layers. But the metals are still visible, still present in the photosphere. This means one thing: ongoing pollution. The white dwarf is actively accreting material, debris from the remains of its planetary system. Asteroids, comets, shattered moons. These rocky bodies spiral inward, tore apart by tidal forces, vaporized by the white dwarf's heat. Their elements mix into the atmosphere. Astronomers can measure diffusion timescales, how long it takes for metals to sink out of sight. If they're still visible, the accretion must be recent, within the last million years, maybe even ongoing now. Some DZ white dwarfs are actively consuming the remnants of worlds. Slowly, atom by atom, the graveyard grows, the metals accumulate, and the white dwarf spectrum tells the story of a destroyed planetary system. There's another rare type, DX white dwarfs. These show both hydrogen lines and metal lines. Hydrogen, calcium, magnesium, together. This is puzzling. If a white dwarf has a hydrogen atmosphere, metals should sink quickly. They shouldn't be visible, unless the accretion is very recent. DX white dwarfs are likely caught in the act. A rocky body has just fallen in. Its debris is still mixing with the hydrogen envelope. Over time, the metals will settle, diffuse downward, disappear from the spectrum. The white dwarf will become a normal DA type again. But for now, for a brief cosmic moment, both signatures coexist. Hydrogen from the star's original envelope, metals from a fallen world. A snapshot, a transition. The white dwarf absorbs, settles, continues cooling, and the metals slowly, invisibly sink into the deep. Some white dwarfs have helium atmospheres for an unusual reason, not because they formed that way, but because they merged. Two white dwarfs, orbiting each other in a tight binary, gradually spiral inward. Gravitational waves carry away energy. The orbit decays. Eventually they collide. They merge. The result is a single white dwarf. Hotter, brighter, with a mixed, disrupted envelope. Often, the merger strips away hydrogen. The combined object is left with a helium-dominated atmosphere. These merger remnants appear unusually bright in ultraviolet surveys. They're hotter than typical white dwarfs of their age. They stand out, anomalies in the population. Over time, they cool, they settle, they fade, but their origin, their violent birth, leaves a signature, a helium atmosphere, a high temperature, a brightness that doesn't quite fit, evidence of a collision, a merging, a transformation, two stars becoming one. Some white dwarfs have a secret. When astronomers observe them in infrared wavelengths, they see too much light, more infrared emission than the white dwarf itself should produce. This is called infrared excess. It means there's dust, a disk of dust, orbiting the white dwarf. This dust comes from asteroids, rocky bodies that were torn apart, ground down into fragments, and spread into a ring. The dust absorbs ultraviolet and visible light from the white dwarf. It heats up, and it re-radiates that energy as infrared light. Telescopes like Spitzer and JWST can detect this mid-infrared glow. The dust disks are often very close to the white dwarf, orbiting just outside the tidal disruption radius. They're the remnants of shattered worlds, the debris of a planetary system, pulverized, scattered, glowing faintly in infrared. Some of these disks are actively feeding the white dwarf. Material spirals inward, accretes onto the surface, pollutes the atmosphere. A slow, continuous consumption. The white dwarf eating its children in cool white dwarfs. Below about 12,000 degrees Kelvin, convection develops in the outer envelope. Convection is efficient. It churns the atmosphere, brings heat to the surface, mixes material, but it has another effect. It dredges up metals. Normally, heavy elements sink. Gravitational settling pulls them down into the deeper layers. Out of sight, but convection counters this. It lifts metals back up, keeps them visible in the photosphere. This prolongs pollution visibility. A white dwarf that accreted rocky debris millions of years ago might still show calcium lines, because convection keeps dredging the calcium back to the surface. The diffusion timescale, the time it takes for metals to sink, becomes effectively infinite. As long as convection operates, the pollution signature remains. The white dwarf spectrum, a permanent record of accretion, not fading, not settling, just visible, persistent, a scar that won't heal. Deep beneath the photosphere of some white dwarfs, metals accumulate. They sink, they settle, they form layers, sediment layers, like geological strata, but made of iron, magnesium, calcium. These layers affect the internal structure. They change the thermal conductivity. They modulate convective flows. In pulsating white dwarfs, these sediment layers can alter the pulsation frequencies. They create resonances, dampening some modes, amplifying others, and spectrally, they can create confusion. A white dwarf with settled metal layers might mimic the appearance of a mixed hydrogen-helium atmosphere. The spectrum looks like both elements are present at the surface, but in reality, It's a layering effect, a stratification. The metals are hidden, buried, but their presence, their mass distribution, affects the light, a subtle deception, a spectral ghost. The white dwarf's interior, hiding information, concealing its composition, while the spectrum tells a slightly false story. Some of the strangest white dwarfs, a tiny fraction, show infrared absorption features that resemble ozone. Ozone, O3, a molecule of 3 oxygen atoms. This is bizarre. White dwarfs shouldn't have ozone. They're too hot, too dense. But the feature is there, unmistakable in some spectra. One hypothesis, still debated, is that these white dwarfs accreted water world planetesimals, planets or moons that were mostly water, ice giants, ocean worlds. When these bodies fell into the white dwarf, they vaporized. The water broke apart. Oxygen was released. In the dense, complex chemistry of the white dwarf's polluted envelope, ozone-like molecules might form. It's speculative, controversial, but tantalizing. The idea that some white dwarfs might have polluted oceans, layers of hydrogen and oxygen, remnants of water from lost worlds, invisible deep beneath the surface, but hinted at by strange absorption features, the ghosts of oceans, the echoes of water, drifting in the spectrum of a dying star. Not all white dwarfs are perfectly steady. Some pulsate. They brighten and dim. Rhythmically, predictably. These are called variable white dwarfs. DAV types if they have hydrogen atmospheres. DBV types if they have helium. The pulsations are caused by oscillations in the star structure. The white dwarf vibrates. Like a bell, like a drum. Gravity waves, pressure waves, modes of vibration running through the degenerate interior. The brightness varies by 1 to 20%. The period, the time for one oscillation, ranges from a few minutes to about half an hour. Astronomers watch these pulsations. They measure the frequencies, the amplitudes, the patterns. This is called astroseismology or stellar seismology. By studying how a white dwarf vibrates, scientists can probe its interior. They can measure the thickness of the envelope, the composition of the core, the rotation rate, the magnetic field. It's like using earthquakes to study Earth's interior. Seismic waves reveal hidden structure. The white dwarf pulsates. The light flickers. And from those flickers, we learn secrets about what lies beneath the surface, about the hidden heart of the dying star. The white dwarf ringing softly, like a distant bell, in the quiet of space. Among pulsating white dwarfs, the most common are the ZZ Ceti stars. These are DA white dwarfs, hydrogen atmospheres, cooling through a specific temperature range, about 12,000 to 11,000 degrees Kelvin. In this zone, something interesting happens. The hydrogen in the envelope undergoes partial ionization. This means some hydrogen atoms are neutral, while others are ionized. Electrons are partially stripped away. This creates an instability. The partially ionized zone acts like a valve. It traps heat, then releases it. Rhythmically, the result is pulsation. The star swells and contracts, ever so slightly. The surface moves up and down by just a few kilometers. But this is enough to change the brightness. ZZ Ceti stars pulsate with periods between 100 and 1,000 seconds, roughly 2 to 15 minutes per cycle. By measuring these periods precisely, astronomers can perform astroseismology. They can map the internal layers, determine the thickness of the hydrogen envelope, probe the boundary between the envelope and the core. The white dwarf vibrates, the light flickers, and from those flickers, we glimpse the interior structure, layer by layer, revealed through mathematics, through resonance. The white dwarf, singing softly, in frequencies of light. Not all pulsating white dwarfs have hydrogen atmospheres. Some, the V777 Hercules stars, or DBV stars, have helium atmospheres. These pulsate in a slightly different temperature range, about 22,000 to 28,000 degrees Kelvin. Here, it's the helium that undergoes partial ionization. Helium has two ionization states: neutral helium, singly ionized helium, doubly ionized helium. The transition zones, where helium shift between these states, create driving mechanisms for pulsation. The pulsation modes in DBV stars reveal the helium fraction in the core, how much helium versus carbon and oxygen. The frequencies are sensitive to composition, to structure, to the exact stratification of elements. Astronomers measure the pulsations, compare them to theoretical models, refine their understanding. Each pulsating white dwarf, a unique laboratory, a natural experiment in dense matter physics. The helium ionizes, the star vibrates, the light varies, and we, distant observers, decode the message, learning about layers we can never see, depths we can never reach, through mathematics, through light, through patient observation. At the hot end of the pulsating white dwarf sequence, there are the GW Virginis variables. These are not typical white dwarfs yet. They're pre-white dwarfs, just transitioning from the asymptotic giant branch. Their surface temperatures range from 75,000 to 170,000 degrees Kelvin. Extremely hot, blue-white, brilliant. Their atmospheres are helium-rich, sometimes carbon-rich, enriched by the final stages of stellar evolution. These stars pulsate due to opacity variations in iron group elements. At certain temperatures and densities, iron partially ionizes. This creates zones where radiation is trapped, then released. The star oscillates, with periods from about 300 to 5,000 seconds. GW Virginis stars offer clues about mass loss, about the transition from giant star to white dwarf, How much mass was shed in the planetary nebula phase? How quickly did the envelope disperse? The pulsations, encoded with this information, the star rings, the frequencies shift, the amplitudes vary, and astronomers listen, measure, model, piecing together the final moments of stellar evolution, the last gasp before silence, before the long, slow cooling begins. There's a special class of pulsating white dwarfs, LMVs, extremely low mass variables. These are white dwarfs with masses below about 0.3 solar masses, much lighter than typical white dwarfs. They form in binary systems. One star strips mass from its companion before the core is fully developed. What remains is a white dwarf with a very thin hydrogen layer, barely any envelope. These thin layers make the stars unstable. They pulsate rapidly. The periods are short, just a few minutes, sometimes less. LMVs offer tests of convective driving theory, the mechanisms that power pulsations. How does convection in an ultra-thin envelope drive oscillations? The models are complex. The observations are challenging. But each LMV, each rapid pulsator, provides data, constraints on theory, tests of physics. The white dwarf, small, light, fragile, vibrates intensely, like a tuning fork, struck and ringing in the cosmic dark. Some white dwarfs are magnetic, not weakly magnetic, but intensely magnetic, fields up to billions of Gauss, 1 billion times stronger than Earth's magnetic field. These fields are so strong they distort the spectral lines. When atoms emit light in a magnetic field, the lines split. This is called Zeeman splitting. Each spectral line, normally a single sharp feature, splits into multiple components. The spacing of these components reveals the field strength. Astronomers measure the splitting, calculate the magnetic field. Some magnetic white dwarfs have fields of 1 million Gauss, others 1 billion Gauss. These fields are so strong, they distort the shape of the white dwarf itself. The magnetic pressure compresses the star along the field lines, stretches it perpendicular to the field. The white dwarf becomes an oblate spheroid, flattened, egg-shaped, not perfectly spherical anymore, deformed by invisible magnetic force. The white dwarf, quietly magnetic, silently distorted, spinning in space. The strongest magnetic white dwarfs, those with fields approaching 1 billion Gauss, have another property. They polarize light. Light is an electromagnetic wave. It oscillates. Normally, the oscillations are random, unpolarized. But in a strong magnetic field, the light becomes organized. The waves align. The light becomes circularly polarized or linearly polarized. This can be detected with special instruments, polarimeters. Astronomers observe the white dwarf, measure the polarization, infer the magnetic geometry. These strong fields also trap and fall material. If the white dwarf is accreting, pulling in gas from a companion star, the magnetic field channels that gas. It doesn't fall uniformly onto the surface. It's funneled into streams, magnetic accretion columns. The gas spirals along field lines, crashes onto the magnetic poles, creating hot spots, X-ray emission, flickering light. The magnetic white dwarf, a cosmic lighthouse, beaming radiation from its poles, spinning, sweeping the beam across space. And we, if aligned just right, see the pulses, the flickers, the rhythm. Not all magnetic white dwarfs are extreme. Some have weak fields, measured in kilogauss, thousands of Gauss, still much stronger than Earth's field, but weak compared to the billion Gauss giants. These weakly magnetic white dwarfs show subtle effects, line broadening, a slight fuzziness to spectral features, no dramatic Zeeman splitting, no obvious polarization, but the magnetism is there, detectable with careful analysis. These white dwarfs bridge the populations between non-magnetic white dwarfs, which make up about 90% of all white dwarfs, and the highly magnetic minority. How do magnetic fields arise in white dwarfs? Some are inherited from a progenitor star, stellar dynamos, fossil fields. Others might form during binary mergers, the chaotic collision amplifying magnetic fields. The origin is still debated, but the weakly magnetic white dwarfs, they hint at a continuum, a spectrum of magnetism, from none to moderate to extreme. The white dwarf, quietly magnetic, subtly marked, carrying invisible fields into the dark future. White dwarfs can spin fast. Some rotate once per second, others even faster. The record holders spin at rates approaching 1 rotation per millisecond, nearly 1 million rotations per second. This is near the breakup speed. Any faster, and centrifugal force would tear the star apart. Why do they spin so fast? Angular momentum conservation. When a star collapses from red giant size down to white dwarf size, it shrinks by a factor of about 100. If the star was rotating even slowly before, when it shrinks, that rotation speeds up like a figure skater pulling in their arms. They spin faster. The white dwarf, condensed, spins rapidly. Over time, magnetic braking and other processes slow it down. But some white dwarfs, especially young ones, or those spun up by accretion, rotate incredibly fast. The surface moves at thousands of kilometers per second. The equator bulges outward. The poles flatten. The white dwarf, a spinning top, a cosmic gyroscope, whirling in the void. White dwarfs are faint. Their small size, their low luminosity, makes them hard to detect. But astronomers have a trick. They look for high proper motion. Proper motion is the apparent movement of a star across the sky. Over years, over decades, nearby objects move more. Distant objects, barely at all. White dwarfs are often nearby, within a few hundred light years. But because they're so faint, they went unnoticed for a long time. By comparing old photographic plates to modern images, astronomers can detect motion, a star that has shifted position, that has moved noticeably, might be a white dwarf. Close, faint, drifting across the sky. This technique has discovered thousands of white dwarfs. Silent, nearby, cooling. They've been there all along, just too dim to see without careful comparison. The white dwarf, sliding slowly against the background stars, barely visible, but moving, a cosmic neighbor, quietly passing by. Some white dwarfs are not alone. They orbit companion stars, closed binaries, two objects locked in gravitational embrace. When the orbit is aligned just right, when we view the system edge-on, we see eclipses. The companion passes in front of the white dwarf. The light dims sharply, then the eclipse ends. The light returns. This happens rhythmically. Every orbit. Astronomers use time series photometry, continuous observation, measuring brightness changes. The depth of the eclipse reveals the white dwarf size. The duration reveals the orbital parameters. From these measurements, precise mass and radius determinations, better than almost any other method. Eclipsing binaries are gold mines of information. Massachusetts radius, orbital period, inclination, everything encoded in the light curve. The white dwarf, periodically hidden, periodically revealed by its companion's shadow. And we, distant watchers, measure the rhythm, decode the geometry, calculate the physics. From flickering light, for centuries, measuring the distance to stars was one of astronomy's greatest challenges. But in recent years, a space telescope called Gaia has transformed everything. Gaia measures parallax, the apparent shift in a star's position as Earth orbits the Sun. It does this with extraordinary precision, down to microarc seconds, a millionth of a degree. For white dwarfs, this is revolutionary. Gaia has precisely mapped distances to hundreds of thousands of white dwarfs. From these distances, astronomers calculate volume densities. How many white dwarfs per cubic parsec? A parsec is about 3.2 light years. Locally, in the solar neighborhood, the density is about 0.01 white dwarfs per cubic parsec. That sounds sparse, and it is. Space is vast, mostly empty, but multiply that density across the entire galaxy, and the numbers become staggering. Billions upon billions of white dwarfs, most too faint to see, too distant to detect. But Gaia, patient precise, has begun counting them, mapping their positions, their distances, their motions, building a census of the dead. Gaia has cataloged over 1 million white dwarfs. 1 million. By combining parallax measurements with photometry, brightness in different colors, Gaia identifies white dwarfs across the sky. The catalog reveals two sequences. A blue sequence, hot young white dwarfs. still glowing intensely from their residual heat, and a red sequence, cooler, older white dwarfs. Fading into the infrared, the distribution traces the history of star formation in the galaxy. Each white dwarf, a timestamp, its cooling age reveals when it formed, which means when its progenitor star died. By studying the white dwarf population, astronomers reconstruct the galaxy's past, when stars formed, when they died, how the stellar population evolved. The white dwarfs, silent witnesses, scattered across the sky, each one carrying a piece of galactic history, and Gaia watching, measuring, recording, building the most complete map of stellar death ever created. Some white dwarfs are invisible in optical light, not because they're too faint, but because they're too hot. The hottest white dwarfs, with surface temperatures exceeding 50,000 degrees Kelvin, emit most of their light in the ultraviolet, the UV, beyond what human eyes can see. In visible light, they appear faint, bluish, unimpressive, but in ultraviolet surveys, like Galex, the Galaxy Evolution Explorer, they blaze. Galex scanned the sky in UV wavelengths, detecting hot stars, hot white dwarfs, objects that optical surveys miss entirely. These surveys reveal populations of young white dwarfs, recently formed, still radiating the intense heat of their birth. They're scattered across the galaxy, marking recent stellar deaths. The white dwarf, glowing ultraviolet, invisible to the eye, but brilliant to the right telescope. A hidden population, revealed by looking in the right wavelength. The universe, full of secrets, hidden in plain sight, waiting for the right eyes to see. White dwarfs of mass, and mass warps space-time. When a white dwarf passes in front of a more distant star, its gravity bends the background star's light. For a brief time, the distant star appears brighter, magnified by the white dwarf's gravitational lens. This is called gravitational microlensing. Astronomers have detected this effect, observing stars toward the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Occasionally, a star brightens, then fades, over days or weeks, the telltale signature of a massive object passing in front. Sometimes, that object is a white dwarf. By studying these microlensing events, astronomers confirm the abundance of white dwarfs in the galactic halo. The halo is the spherical region surrounding the Milky Way's disk. Old, metal-poor, sparsely populated, but white dwarfs are there, ancient ones, from the galaxy's earliest stars. Invisible, too faint to detect directly, but revealed momentarily by their gravitational influence, bending light, magnifying distant stars, a ghost in the dark, detected by its gravity. The galactic halo contains mysteries. One of them is a population of very old white dwarfs. These are not part of the disk. They orbit in the halo, in eccentric, tilted paths. They're ancient, formed billions of years ago. Some may be remnants of dissociated globular clusters. Globular clusters are dense spheres of old stars. Hundreds of thousands of stars, packed tightly together. Over billions of years, some globular clusters dissolve. Tidal forces from the galaxy strip away their stars. The stars scatter, disperse into the halo. Many of those stars have already died, become white dwarfs. These halo white dwarfs, faint beyond detection, occasionally reveal themselves through microlensing, magnifying stars in the galactic bulge, the dense central region of the Milky Way. The microlensing events are rare, brief, but they confirm the halo is filled with invisible white dwarfs, an ancient population, drifting, silent, the remnants of the galaxy's first stars, cooling for over 10 billion years. Within 100 light years of Earth, there are about 10,000 white dwarfs. 10,000. Most are unknown, undetected, too faint to see even with powerful telescopes. A few hundred have been cataloged, measured, studied, but the majority remain invisible. They're there, cooling quietly, orbiting the galaxy, but their light, too dim to reach us with enough intensity to register. Multiply this locally across the entire Milky Way. The galaxy is roughly 100,000 light years across. Trillions of white dwarfs scattered throughout the disk and halo. An invisible graveyard, outnumbering the living stars in some regions. We walk through a galaxy filled with the dead, stellar corpses, cooling, fading, all around us, unseen, the white dwarfs silent, numerous, hidden in the darkness between the stars. Old white dwarfs are valuable, not for their light, but for their age. The oldest white dwarfs, those in the galactic halo, have been cooling for over 10 billion years. Their temperatures, their luminosities, their cooling curves, all of these encode their age. By measuring the faintest, coolest white dwarfs in the halo, astronomers date the galaxy itself. When did the first stars form? When did the first white dwarfs appear? The cooling sequences act as a cosmic clock. The faintest white dwarfs, the oldest ones, set a lower limit on the age of the Milky Way. Current estimates, based on halo white dwarfs, suggest the galaxy is at least 12 to 13 billion years old, formed not long after the Big Bang, in the early universe. The white dwarfs, ancient timekeepers, their faint glow, a time stamp from the distant past, still cooling, still fading, but still, after all these eons, carrying the memory of the galaxy's birth. Globular clusters are among the oldest objects in the galaxy. Dense, spherical, ancient, they contain white dwarfs. Many white dwarfs. By studying the white dwarf cooling sequence in a globular cluster, astronomers can determine the cluster's age. Take NGC 6752. A globular cluster in the southern sky. Its white dwarfs have been cooling for over 11 billion years. The faintest white dwarfs, the coolest ones, are at the lower limit of detectability. By comparing their properties to theoretical cooling models, astronomers pin the cluster's age at 11 to 13 billion years. This is consistent across multiple globular clusters. They're all old, formed in the early universe. The white dwarfs, cooling relics, confirm this, precise age indicators, better than many other methods. Each faint white dwarf, a clock, ticking slowly, marking the passage of cosmic time. The faint end of the white dwarf luminosity function in the galactic disk reveals something important. There's a cutoff below a certain luminosity. White dwarfs become extremely rare. This cutoff corresponds to an age, about 8 to 11 billion years. What does this mean? It means the disk, the flat, rotating structure of the Milky Way, stopped forming stars rapidly around 8 to 11 billion years ago. Star formation didn't cease entirely, but it slowed. The rate dropped. The oldest white dwarfs in the disk formed from stars that lived and died during that early period. Their faintness, their extreme age, sets a boundary, a marker when the disk's stellar population began. The white dwarfs, ancient, faint, barely glowing, tell the story of the galaxy's youth, when stars formed in great bursts, then slowed, settled into the gradual pace we see today. Open clusters are different from globular clusters. They're younger, looser, fewer stars, but they're useful because they're stars all formed at the same time. In the Hyades cluster, one of the nearest open clusters to Earth, astronomers have identified white dwarfs. These white dwarfs descended from the most massive stars in the cluster, the stars that live fast, died young. By studying where the white dwarf sequence cuts off, where there are no fainter white dwarfs, astronomers determine when the cluster formed. The Hyades, precisely 625 million years old. The white dwarfs, markers of stellar lifetimes. The most massive stars lived about 600 million years, then died, became white dwarfs. Those white dwarfs have been cooling ever since. Their properties, their temperatures, their luminosities encode the cluster's age with remarkable precision, better than almost any other method. The white dwarfs, timekeepers, age indicators, cooling slowly, recording history. In their fading light, breathe slowly now, in and out. The white dwarfs cool. Time passes, and you rest, safe, comfortable, drifting into the quiet dark where the white dwarfs wait. Patient, silent, forever cooling. In the globular cluster M4, astronomers have resolved individual white dwarfs. M4 is relatively nearby, about 7,000 light years away, close enough that powerful telescopes, like the Hubble Space Telescope, can pick out individual cooling white dwarfs. By measuring these white dwarfs, their masses, their cooling ages, astronomers derive something crucial: the initial final mass relation. This relationship connects a star's initial mass, when it first formed, to its final mass as a white dwarf. A star born with 3 solar masses becomes a white dwarf of what mass? 0.6? 0.7? The answer depends on mass loss. How much material the star shed during its red giant and asymptotic giant branch phases. M4's white dwarfs validate theoretical prescriptions, models of AGB mass loss. The observations match predictions. The models, refined over decades, hold up each white dwarf in M4 a data point, a confirmation of stellar evolution theory. The cluster ancient resolved offers a laboratory where theory meets observation, and the white dwarfs, cooling slowly, confirm our understanding of how stars die, how they shed their envelopes, how they become embers. In any globular cluster, the white dwarf luminosity function is a powerful tool. The luminosity function is simply a count. How many white dwarfs at each brightness level? Bright white dwarfs, intermediate white dwarfs, faint white dwarfs. The distribution, the shape of the function, reveals the cluster's age. Because white dwarfs cool predictably, their luminosity decreases with time. If a cluster has no white dwarfs fainter than a certain threshold, it means the cluster isn't old enough for any white dwarf to have cooled that much yet. This sets a lower limit on the cluster's age. For example, if the faintest white dwarf has been cooling for 12 billion years, the cluster must be at least 12 billion years old, probably older, because the progenitor star had to live its life first. White dwarf luminosity functions, cosmic clocks, reliable, precise. The faint end, the cutoff, marks time. The cluster's age, written in fading light. The Milky Way has structure, a thin disk, where most stars orbit in roughly circular paths, and a thick disk, older stars, orbiting with more random motions. White dwarfs in the thick disk show distinctive kinematics. Their tangential velocities, the component of motion perpendicular to our line of sight, peak at around minus 150 kilometers per second. This signature, this velocity distribution, traces ancient events, merger events, billions of years ago, when smaller galaxies collided with the Milky Way, disrupted, dissolved, their stars scattered into the thick disk. Those stars have since died. Many became white dwarfs, and those white dwarfs still carry the velocity signature, the orbital memory of a merger that happened 10 billion years ago. The white dwarfs, ancient, fast-moving, ghosts of galaxies long destroyed, still orbiting, still carrying the scars of cosmic collision in their motion, their speed, their trajectories. Some white dwarfs move very fast, not just the typical orbital speeds, but extreme velocities, up to 500 kilometers per second. These high-velocity white dwarfs dwarfs dominate the tail of the velocity distribution. Why so fast? One explanation: asymmetric planetary nebula ejections. When a star sheds its envelope, forming a planetary nebula, the ejection isn't always symmetric. If more material is thrown in one direction, the star recoils. Like a rocket, the white dwarf, the leftover core, gets kicked, accelerated to high speeds by the asymmetric mass loss. It flies through the galaxy, fast, solitary, a runaway remnant. These high-velocity white dwarfs, scattered across the Milky Way, moving too fast to stay bound to their birthplaces, drifting through the disk, the halo, solitary travelers, kicked by their own death throes into the cosmic dark. And then there are the hypervelocity white dwarfs, even faster, over 1,000 kilometers per second. So fast, they're escaping the galaxy entirely. These are rare, extraordinary. One formation mechanism, the Hill's mechanism. Imagine a binary system. Two white dwarfs orbiting each other, deep in the galactic center. The supermassive black hole, Sagittarius A star, lurks nearby. The binary wanders too close. The black hole's gravity disrupts it. One white dwarf falls toward the black hole, captured. The other flung outward, ejected at incredible speed, over 1,000 kilometers per second. It races through the galaxy, outward, upward. Eventually, it will leave the Milky Way, escape into intergalactic space, a hypervelocity exile, kicked by a black hole, fleeing the galaxy. The white dwarf, alone, fast, unstoppable, heading into the void between galaxies, where it will cool, alone, forever. Some white dwarfs in the solar neighborhood move unusually fast. Runaway white dwarfs, speeds of 100 to 300 kilometers per second. Their origins likely tied to Type Ia supernovae. A Type Ia supernova happens when a white dwarf in a binary system accretes matter, reaches critical mass, explodes. But what happens to the companion star? It survives, and it gets kicked. The explosion is asymmetric. The companion is accelerated, flung away. If the companion is also a white dwarf, or becomes one later, it becomes a runaway. Astronomers find these objects, white dwarfs with high velocities, moving away from known supernova remnants, tracing back their trajectories. They converge on explosion sites, evidence of past violence. The white dwarf, a survivor, ejected by his companion's death, now alone, fast-moving, carrying the memory of an explosion in its velocity, its trajectory. In young star clusters, interactions are common. Stars pass close to each other. Gravitational encounters. Three-body interactions. Sometimes a white dwarf gets ejected, kicked out of the cluster at speeds of 100 to 300 kilometers per second. These ejected white dwarfs trace the dynamics of star formation. They reveal how clusters evolve, how stars scatter, how energy is exchanged. Some ejections are linked to supernova remnants. When a massive star explodes, the explosion is asymmetric. The neutron star or black hole remnant gets kicked in one direction, but the surrounding stars also feel effects, acceleration, perturbations. White dwarfs formed in these environments might be flung away, their velocity vectors pointing back to the remnant, evidence of the explosion's asymmetry. The white dwarf ejected, fast-moving, a witness to stellar violence. Not all white dwarfs cool alone. Some are in binary systems, orbiting companion stars. And in these systems, something dramatic can happen. The white dwarf, with its intense gravity, can siphon material from its companion. Hydrogen gas streams across the gap, falls onto the white dwarf surface. Slowly, over years, decades, a layer of hydrogen accumulates, compressed, heated by the white dwarf's residual warmth and gravitational energy. Eventually, the layer reaches critical density and temperature, and it ignites, not gradually, but explosively. A thermonuclear runaway, a nova, the surface of the white dwarf flares, brightens by factors of 10,000, 100,000. For weeks, the nova shines, then fades, but the white dwarf survives. The explosion happens only on the surface. The core remains intact, and the process can repeat. The white dwarf accretes more material, builds another layer. Decades or centuries later, another nova, the white dwarf, a repeating bomb, flashing in the darkness. Binary systems with accreting white dwarfs have a special name: cataclysmic variables, CVs. These systems feature a white dwarf pulling material from a low-mass companion, a red dwarf, or a subgiant. The transfer material doesn't fall directly onto the white dwarf. It spirals, forms an accretion disk, a swirling ring of hot gas. The disk glows, emits X-rays, ultraviolet light. Over time, material from the disk spirals inward, settles onto the white dwarf, building an unstable hydrogen shell. When conditions are right, the shell detonates. A classical nova. Bright, sudden, the system flares, ejects material, then settles back down. The accretion resumes, the disk reforms, and the cycle continues. Cataclysmic variables are laboratories for studying accretion, binary evolution, thermonuclear explosions, each nova a test of physics. The white dwarf patient, accreting, building toward the next outburst. There's a rare type of binary, AM-CVN systems, named after the prototype AM Canum Venaticarum. In these systems, both objects are white dwarfs, or one is a white dwarf and the other is a helium-rich remnant. The key difference: there's no hydrogen. The transfer material is pure helium. Helium streams from the donor onto the accreting white dwarf, forms a helium accretion disk. Over time, helium accumulates on the white dwarf surface, compressed, heated, and eventually it ignites. A helium flash, a helium nova, pure helium fusion, bright, transient. These events are rare, hard to detect, but spectacular. AM-CVN systems, exotic binaries, helium transferring, helium igniting, no hydrogen, just a fusion of helium into carbon. The white dwarf, accreting, exploding, surviving, in a dance with its helium-rich companion, over and over, for millions of years. Some white dwarfs orbit giant stars, not red dwarfs, not main sequence stars, but giants, bloated, luminous. These are called symbiotic systems. The giant star, puffed up and losing mass, sheds material through a stellar wind. The white dwarf, orbiting nearby, accretes this wind, but the accretion rate is different from cataclysmic variables. It's steady, continuous, gentle. The hydrogen accumulates on the white dwarf surface, but doesn't build up to explosive ignition. Instead, it burns stably, a steady nuclear burning shell, hydrogen fusing into helium at the surface. This makes the white dwarf appear brighter, hotter. The system can mimic mirror variables, long-period pulsating giants. But the light curve, the spectrum, reveals the binary nature. Two components, giant and white dwarf, locked together. The giant feeding the white dwarf, the white dwarf burning steadily. A symbiosis, a mutual dependence. The white dwarf glowing from accretion, not from residual heat, but from fresh fuel, stolen from its giant companion. Many white dwarfs orbit main sequence stars. The companion, a normal star, burning hydrogen in its core. For now, the system is detached. The stars don't touch. But over time, things change. The companion evolves, expands, ages, and the orbit shrinks, magnetic braking. Angular momentum is lost through magnetic interactions with stellar winds. The orbital period decreases. The stars spiral closer. Eventually, the companion's outer layers reach the white dwarf. Contact, Roche lobe overflow, mass transfer begins. The system becomes a cataclysmic variable. This evolution, from detached binary to CV, is common. Astronomers observe systems at different stages, some just beginning mass transfer, others well established. The white dwarf patient, waiting as its companion ages, expands, and eventually begins to feed it. The transformation, slow but inevitable, written in orbital mechanics. Some white dwarf binaries orbit very close, so close that their orbital periods are measured in minutes or hours. These type binaries emit gravitational waves, ripples in space-time, predicted by Einstein. confirmed by LIGO, as the binaries emit gravitational waves. They lose energy, the orbit shrinks, the period decreases. Over millions of years, the white dwarfs spiral closer and closer. Future space missions, like LISA, the Laser Interferometer Space Antenna, will detect these systems, thousands of them, scattered across the galaxy, each one a source of gravitational waves. By measuring the wave frequency and amplitude, astronomers can predict merger times. When will the two white dwarfs collide? In 1,000,000 years? 10 million? The gravitational waves encode this information. A countdown written in space-time curvature. The white dwarfs orbiting, radiating, slowly spiraling toward merger. Inevitable, patient, unstoppable. Some white dwarfs orbit pulsars. Not just any pulsars. Millisecond pulsars. These are neutron stars spinning hundreds of times per second, rapidly rotating, emitting beams of radio waves. The white dwarf, a quiet companion, but its presence reveals a history. The pulsar wasn't always spinning this fast. It was spun up, recycled, by accreting material from the white dwarf's progenitor. When the companion was a red giant or subgiant, it transferred mass to the neutron star. The neutron star accreted, spun faster, became a millisecond pulsar. Then the companion, stripped of its envelope, became a white dwarf. Now the system is detached. The pulsar spins. The white dwarf cools. These systems constrain binary evolution models. How does accretion spin up a neutron star? How much mass was transferred? At what rate? The tight orbits, the white dwarf masses, provide clues. Each system a fossil record of mass transfer, of recycling, of evolution. The white dwarf silent witness to its companion's transformation. Some white dwarf binaries are not alone. They orbit in hierarchical triples. Two white dwarfs close together. A third star farther out. The outer star's gravity perturbs the inner binary. It induces oscillations in eccentricity and inclination, correlative cycles. The inner binary's orbit becomes highly elliptical, then circular again, repeating over long timescales. During high eccentricity phases, the white dwarfs pass very close to each other. Tidal forces, gravitational wave emission, energy loss, the orbit shrinks. Eventually, the oscillations destabilize the system. The two white dwarfs merge. These mergers, predicted by simulations, might produce exotic transients, fast radio burst precursors, unusual optical flares. The white dwarfs, driven together, not by their own orbital decay, but by the distant perturbations of a third star, a cosmic dance, three bodies, chaotic, inevitable, leading to collision. When two white dwarfs merge, the outcome depends on their masses. If both are relatively low mass, the merger can produce something strange. On our Corona Borealis star, our CRB stars are rare, hydrogen poor, carbon rich. They show dramatic brightness variations, sudden dimming events. The dimming, caused by clouds of carbon dust, ejected from the surface, obscuring the star. The merger of two helium white dwarfs, or a helium and carbon oxygen white dwarf, can create this composition. Hydrogen is depleted, carbon is abundant. The merged object, hot, unstable, throws off material, forms dust, fades, brightens again. Our CRB stars, exotic, beautiful, unpredictable, born from a violent collision of white dwarfs. The white dwarfs, no longer separate, merged, blended, transformed into something new, something strange, a carbon star, dusty, variable, still evolving, still settling. Not all white dwarf mergers produce our CRB stars. Some produce massive white dwarfs, over 1 solar mass, sometimes 1.2, 1.3. These remnants spin rapidly. The merger imparts angular momentum, rotation rates, hundreds of times per second initially. The atmosphere distorted, oblate, flattened by centrifugal force. Viscosity reshapes the structure, redistributes mass. Over time, the remnant settles, cools, but it remains massive, close to the Chandrasekhar limit. These objects are candidates for a future type Ia supernovae. If they accrete more mass from a companion, they might reach critical mass and explode. The merger remnant, a ticking bomb, slowly accreting, slowly approaching instability. The white dwarf, massive, spinning, waiting for the final push. In surveys, astronomers occasionally find ultramassive white dwarfs, masses near 1.2 solar masses, very close to the Chandrasekhar limit. These are unusual. Most white dwarfs are around 0.6 solar masses. The ultramassive ones often have oxygen neon magnesium cores, formed from intermediate mass progenitors. Some might be merger remnants, two white dwarfs combined. Their high mass hints at complex histories, binary interactions, accretion, collision. These white dwarfs edge close to instability. A little more mass, and they would collapse or explode. They sit on the brink, massive, dense, quiet, but fragile, precarious, one perturbation away from catastrophe. Type Ia supernovae are cosmic distance markers. They explode with consistent brightness, standardizable candles, used to measure the expansion of the universe. But what causes them? The leading model, a white dwarf accreting from companion, hydrogen, helium, carbon. Over millions of years, the white dwarf's mass increases, approaches the Chandrasekhar limit, 1.4 solar masses. At this critical mass, the core can no longer support itself. Electron degeneracy pressure fails. The core collapses, heats, ignites, carbon fusion, runaway, explosive. Within seconds, the entire white dwarf detonates, blown apart, shredded into space, releasing the energy of billions of suns. A Type Ia supernova, bright, brief, uniform, the white dwarf obliterated, but its explosion standardized, useful for measuring cosmic distances, revealing the universe's expansion, its acceleration, dark energy, all from the death of a white dwarf. Not all accreting white dwarfs explode. Some collapse. If the white dwarf is made of oxygen, neon, and magnesium, and it approaches the Chandrasekhar limit, electron capture can occur. Electrons are captured by neon and magnesium nuclei, converted into neutrons. This reduces the electron degeneracy pressure. The core can no longer support itself. It collapses, not explosively, but implosively. The white dwarf compresses, shrinks, becomes a neutron star. During the collapse, the degenerate matter decompresses explosively. Nuclear reactions, heavy element synthesis. Our process elements, rare, precious, gold, platinum, uranium, created in the collapse, ejected in a brief burst. The white dwarf transformed, no longer a white dwarf, now a neutron star. Denser, smaller, spinning, a transformation, a metamorphosis, from one kind of stellar corpse to another. Breathe deeply, in and out, the white dwarfs merging, collapsing, exploding in the vast cosmos, transforming, and you resting, safe, drifting through these quiet facts. No explosions here, just gentle descriptions of distant cosmic events. Let your mind wander. Let sleep come. The white dwarfs continue their journey, and so do you, into rest, into dreams. Imagine a binary system, a white dwarf orbiting a neutron star, two stellar corpses, locked together by gravity. Over millions of years, they emit gravitational waves. The orbit decays, shrinks. Eventually, they merge. The collision is violent, asymmetric. The white dwarf, less dense than the neutron star, is torn apart, shredded by tidal forces. The neutron star accretes some material, spins faster, but much of the white dwarf debris is ejected. This ejecta undergoes rapid neutron capture. Our process nucleosynthesis, creating heavy elements, gold, platinum, rare earths. The merger produces a kilonova, a brilliant infrared transit, and sometimes a long-duration gamma-ray burst, a jet of radiation beamed into space, visible across the universe. The white dwarf obliterated, transformed into heavy elements. The neutron star spinning faster, enriched, a violent union, creating the universe's heaviest atoms. After a white dwarf neutron star merger, the neutron star survives, spinning rapidly, a pulsar, beaming radio waves across space. But the debris from the white dwarf doesn't disappear. It forms a disk around the neutron star. Over time, this disk cools, condenses, forms planets, pulsar planets. The most famous example, PSR B 1257 plus 12, a millisecond pulsar with at least 3 planets orbiting it. These planets are small, rocky, dead, orbiting in the intense radiation of the pulsar. They likely formed from the debris of a destroyed companion, a white dwarf, or a main sequence star shredded during the pulsar's formation. The planets, second-generation worlds, born from stellar death, orbiting a cosmic lighthouse, bathed in radiation, lifeless, but real. The white dwarf, its atoms scattered, some consumed by the neutron star, others reformed into planets, a strange rebirth. Not all white dwarfs die quietly. Some 1 or 2 close to supermassive black holes, the kind that lurk at the centers of galaxies, millions, sometimes billions of times the mass of the sun. As the white dwarf approaches, tidal forces increase. The side closer to the black hole feels stronger gravity than the far side. The white dwarf stretches, deforms, and at a critical distance, the tidal disruption radius, it tears apart, shredded into a stream of gas. This gas spirals into the black hole, forms an accretion disk, heats to millions of degrees, emits X-rays, bright, sudden. The spectrum shows iron lines, broadened by relativistic effects, Doppler shifts, gravitational redshifts. The white dwarf consumed, its atoms falling into black hole's event horizon, some escaping as radiation, most lost forever, a bright flare, a tidal disruption event, marking the end of a white dwarf's long journey. In the galactic center, where stars are densely packed, collisions happen. Sometimes, a white dwarf collides with a red giant. The collision is chaotic, asymmetric. The white dwarf, plowing through the giant's extended envelope. Material is shocked, heated, compressed. Nuclear reactions ignite. Calcium is synthesized. The result is a calcium-rich transient, a faint supernova-like explosion, but different. Low ejector velocities, high metallicity, rich in calcium and other intermediate mass elements. These events are rare, faint, hard to detect, but they hint at the violent dynamics of dense stellar environments. The white dwarf, perhaps surviving, perhaps destroyed. The red giant disrupted, stripped, and a brief flash of light, announcing the collision, the synthesis of calcium, the scattered debris. In the crowded heart of the galaxy, future gravitational wave detectors, operating in the decihertz range, will open new windows. DOPT Desigo. Others. These missions, designed to detect frequencies between LIGO and LISA. In this range, neutron star, white dwarf binaries shine, especially during Roche lobe overflow, when the white dwarf begins transferring mass to the neutron star. The system's orbital frequency, its gravitational wave signal, evolves rapidly. DOPT could detect thousands of these systems every year, watching them in real time as they spiral, as they merge, mapping their distribution across the galaxy, testing binary evolution models, measuring merger rates. The white dwarfs, singing in gravitational waves, about to be consumed by neutron stars, and we listening with detectors in space, attuned to the ripples in space-time, counting the doomed binaries, learning how stars die. Together, LISA, the Laser Interferometer Space Antenna, will launch in the coming decades. 3 spacecraft, millions of kilometers apart, forming a triangle in space, listening for gravitational waves. LISA will resolve thousands of white dwarf binaries, especially in the galactic core, where stars are densest. Each binary a unique gravitational wave source. LISA will measure their frequencies, their amplitudes, their evolution, mapping the distribution of white dwarf binaries, calculating merger rates, testing general relativity in strong field regimes where space-time is curved, warped, the white dwarfs orbiting close, emitting waves, and LISA detecting them one by one, thousands, building a map of death, of gravity, of cosmic choreography. The white dwarfs unaware, just orbiting, but their gravity sends ripples across space, and we will listen and learn. Many white dwarfs show metal pollution, calcium, magnesium, iron, silicon in their spectra, in their atmospheres. These metals come from outside, from asteroids, planetesimals, rocky debris, remnants of the white dwarf's planetary system. When the star became a red giant, it disrupted its planets, scattered them. Some were ejected, others sent inward. Over millions of years, these rocky bodies spiral into the white dwarf, torn apart by tidal forces, vaporized by heat. Their elements mix into the atmosphere, creating a signature, a chemical fingerprint. Astronomers can read this fingerprint, determine the composition of the original asteroid or planet. Was it rocky, icy, metallic? The white dwarf, a cosmic graveyard, consuming the remnants of its planetary system, and in doing so, revealing what those worlds were made of. Some white dwarf pollution might come from interstellar sources, rogue planets, high-velocity asteroids, objects not bound to the white dwarf, but passing through, captured by gravity, falling inward. These events would be sporadic, unpredictable, a sudden influx of metals, then silence, slow diffusion. The metals sink, disappear from the photosphere. Years or centuries later, another event, another rogue object, another pulse of pollution. This could explain some observed variability. White dwarfs whose metal content changes, fluctuates, not from a stable debris disk, but from random encounters. The white dwarf, a gravitational sink, capturing whatever drifts too close. Interstellar debris, orphaned worlds, consuming them, briefly glowing with their elements, then fading again into the quiet dark. The spectra of polluted white dwarfs reveal extraordinary details, not just which elements are present, but their ratios. High iron to magnesium ratios, high aluminum content. These signatures suggest differentiated rocky bodies, planets or asteroids that had geologically active histories, molten cores, mantles, crusts like Earth, layers separated by density. When such a body falls into a white dwarf, its crust vaporizes first. The white dwarf spectrum reflects the crust composition, exotic minerals, mantle rocks, from exoplanets we will never see, worlds destroyed long ago, their atoms scattered, but their chemistry preserved. In the fading light of a white dwarf, we can study the geology of dead planets by analyzing the polluted atmospheres of their killer stars. The white dwarf, an archive of planetary science. From worlds light years away, the James Webb Space Telescope, JWST, has opened new possibilities. It can observe in the infrared with extraordinary sensitivity, and it can detect subtle signals, like planets orbiting white dwarfs, especially planets in the habitable zone, the region where liquid water could exist. For a white dwarf, the habitable zone is close, very close, because white dwarfs are faint. A planet would need to orbit within a few million kilometers. JWST can detect these planets through infrared excess. The planet, warmed by the white dwarf, emits infrared radiation. This blends with the white dwarf's light, but careful analysis, spectral modeling can separate the signals. Some white dwarfs might host Earth-like planets, rocky worlds in the habitable zone, orbiting close, tidally locked perhaps, but potentially warm, potentially capable of holding atmospheres. The white dwarf, a second chance for life, or just a curiosity, a strange outcome of planetary dynamics. We don't know yet, but JWST is looking, searching for these hidden worlds, orbiting the cooling embers of dead stars. Breathe slowly now, in and out. We're approaching the end. Just 10 more facts about white dwarfs and black dwarfs, the cooling remnants, the fading light. Let yourself drift deeper. The facts wash over you like gentle waves. No need to hold on. No need to remember. Just rest and listen. Imagine a rocky planet, Earth-sized, orbiting a white dwarf. Not far out, but close, very close. Between 0.01 and 0.05 astronomical units. That's the habitable zone for a white dwarf, the region where temperatures allow liquid water. How could such a planet exist? It would need to survive the red giant phase, when the stars swelled, engulfed the inner planets. Perhaps this planet migrated outward, pushed by gravitational interactions. Or perhaps it formed later from debris. Either way, it's there now, orbiting close, receiving Earth-like insolation, warmth, gentle light. For billions of years, this planet could remain habitable. As the white dwarf cools slowly, the planet a second chance, a world reborn, in the habitable zone of a dying star. Could life emerge? Could it persist? We don't know, but the possibility is there. Quiet, patient, waiting. JWST, the James Webb Space Telescope, has already begun finding them, candidate planets, around nearby white dwarfs, using its MIRI instrument, mid-infrared imaging. JWST detects thermal emission, heat radiated by the planet. This emission exceeds the white dwarf's Rayleigh Jean's tail. The expected infrared glow from the white dwarf alone. The excess indicates a planet, warm, close, orbiting. The first candidates are being analyzed now. Spectra, light curves, confirmation. These planets, if confirmed, would be extraordinary. Worlds surviving stellar death, orbiting embers, bathed in faint light, and we, for the first time, are detecting them with infrared eyes, peering into the habitable zones of white dwarfs. The future holds more discoveries, more worlds, more possibilities around the fading stars. Now, let's look far into the future. Trillions of years from now, 10 to the power of 15 years, 1 quadrillion years. The universe is ancient, dark, cold. All the stars have burned out. All the white dwarfs have cooled completely. They emit no radiation, no light, no heat. They are black dwarfs, cold, degenerate matter, hovering near absolute zero, still massive, still dense, but invisible, silent, inert. The black dwarf retains the mass of the white dwarf it once was, but it glows no more. No fusion, no residual heat, just existence. A sphere of carbon and oxygen, or oxygen and neon, crystallized, frozen, the universe's ultimate stellar graveyard, where nothing burns, nothing shines, just cold, dark, matter, waiting for what comes next. Black dwarfs represent the end of stellar evolution, but they are not the end of the universe's story. They simply exist for unimaginable timescales. 10 to the power of 15 years. To cool completely, 10 to the power of 24 years. To begin changing again. These numbers are beyond comprehension. The current universe is only 14 billion years old. 10 to the 9 years. 10 to the power of 15 is 1,000,000 times longer than the entire history so far. In that distant future, galaxies have dissolved. Black holes have evaporated. Only the black dwarfs remain, scattered, isolated, drifting through the void. In a universe so old, so cold, so empty, that time itself seems to slow. The black dwarfs, patient beyond measure, waiting for the next transformation, even in the extreme cold of a black dwarf. Matter is not entirely static. At temperatures near absolute zero, quantum tunneling allows reactions, picnonuclear reactions. The immense pressure inside the black dwarf brings nuclei close together, so close that quantum mechanics allows them to fuse, even without heat, over timescales of 10 to the power of 24 years. Carbon nuclei tunnel together, fuse into heavier elements, oxygen, neon, magnesium, eventually iron. The black dwarf slowly becomes iron-dominated. This is not a fast process, not an energetic one, just slow, inevitable, quantum. The black dwarf transforming from carbon-oxygen to iron over eons beyond eons, in the deep cold of the far future, after 10 to the power of 40 years, an incomprehensible span of time, something unexpected happens. Uranium, trace amounts, present in the black dwarf, begins to fuse, again through picnonuclear reactions, quantum tunneling at immense pressure. Uranium nuclei tunnel together, release energy. For a brief moment, cosmically brief, the black dwarf reignites. A flicker of heat, a pulse of radiation. Then it fades again, back into darkness. The final gasp, the last emission, before the universe's heat death. The black dwarf, glowing once more, for an instant, in the inconceivable future. Then silence, forever, after 10 to the power of 10 to the power of 26 years. A number so large, it's almost meaningless. Written as 1 followed by 10 to the 26 zeros, the black dwarf undergoes another transformation. Electron capture. Electrons captured by iron nuclei, converting protons into neutrons. The electron degeneracy pressure fails. The black dwarf collapses, compressing into dense clumps, almost like primordial black holes, but not quite. Strange, exotic, quantum. The matter reorganizes into configurations unknown today. The black dwarf, no longer sphere, but fragments, clumps, dense packets of matter, drifting, collapsing in the unimaginable future. Some theories predict that after 10 to the power of 1,000 years, the black dwarf, or what remains of it, might slowly fission, breaking apart into smaller clumps. This is speculative, based on extreme quantum effects, hawking radiation-like processes in regimes we barely understand. The dense matter tunnels, decays, fragments, over timescales so long, they dwarf everything discussed so far. 10 to the 1,000th power, a number with 1,000 zeros. The black dwarf dissipating, not through heat, not through radiation, but through quantum decay. Slow, inevitable, strange. The final breakdown of matter itself. After 10 to the power of 100 years. Another theory suggests the black dwarf evaporates through quantum tunneling. Particles tunnel out of the dense structure. Positrons, electrons, neutrinos release slowly, randomly. The black dwarf losing mass, atom by atom, over Gauss-year timescales. The universe's final energy dispersal, the last whispers of matter, converting into radiation, into particles, into nothing. The black dwarf, fading not through cooling, but through decay, through tunneling, into the quantum foam. The universe approaching its end, and the black dwarfs, the last remnants of stars, dissolve into the void. And finally, the last fact, after 10 to the power of 34 years, if protons decay, as some theories predict, the black dwarf structure destabilizes. Protons, the building blocks of atomic nuclei, decay into lighter particles. Positrons, neutrinos, the iron nuclei break apart. The degenerate structure collapses. The black dwarf disintegrates, not explosively, but gradually, atom by atom, nucleus by nucleus, until nothing remains, just radiation, energy, scattered across infinite space. The black dwarf, the final form of a star, dissolves, returns to the quantum vacuum, the end of stellar evolution, the end of matter itself. And the universe continues, empty, dark, expanding forever into the infinite cold. The white dwarfs, the black dwarfs, all gone, return to nothing after journeys lasting longer than time itself. And now, dear listener, our journey ends. 100 facts about white dwarfs and black dwarfs from their formation billions of years ago to their dissolution in the inconceivable future. You've drifted through cosmic time, through stellar death, through the patient cooling of a universe. Rest now, let sleep come fully. The white dwarfs continue their journey without you, cooling, fading, waiting in the vast, patient cosmos, and you safe, comfortable, at peace, drift into dreams. Good night.